Hello, here is your Unit 3 review for Chem 110. I would suggest that you have paper and pencil and a calculator so that as I present various problems and questions, you can practice those, write down your ideas, and review what you learn. All right, so let's go ahead and get started with Unit 3. Remember that in Unit 3, we're looking at the states of matter, the balances between the intermolecular forces and kinetic energy that cause our various states of matter. We're looking at the gas laws, of course, since gases are one of our states of matter, and solutions. So let's get started. So which one of these states of matter has the greatest intermolecular force? Hopefully you were thinking solids, right? And if you're looking at that solid, you can see those black lines there. Those are the intermolecular forces. And we'll review those intermolecular forces very soon. Remember that we have three intermolecular forces. London dispersion for your nonpolar molecules, dipole-dipole for your polar molecules, and then a special dipole-dipole called hydrogen bonding for your polar molecules that have hydrogen bonded to FO or N. And so keep in mind that in order for the solid particles pictured here to break away and become a liquid and a gas, they're going to have to break those black lines, those intermolecular forces that you can see there, to escape their solid form. And so there's going to be a balance there between the intermolecular forces and the kinetic energy. The greater the intermolecular forces, so if you have a very polar molecule, one with a very large electronegativity difference, it's going to require more energy for that molecule to melt or evaporate. And that molecule is also, that substance is also going to have greater viscosity and things like that. So make sure you review what factors affect those intermolecular forces, like we just did here. All right, so which state of matter has the lowest intermolecular force? Hopefully you were thinking the gas, like this one pictured here. And ideally, and obviously this looks like an ideal gas, there are no intermolecular forces there. And that's why you have no black lines there. All right, so let's take a look if you can determine the various intermolecular forces for these three molecules. This is a great time to pause the video. So remember that in order to do this, you first need to visualize what these molecules look like. You need to visualize their shape and the electronegativity difference. So the first one, since it's just O2, would look like this. A linear molecule, no difference in electronegativity between the two oxygen atoms. So our only intermolecular force there is going to be London dispersion. And then, of course, you're going to need to think about what does PCl3 look like? Hopefully you're thinking that. It is a trigonal pyramidal molecule, as you can see there. So is it polar? What is our electronegativity difference? So let's take a look at that. It is going to be a polar molecule because we're going to have a pretty big electronegativity difference, 0.97, so greater than 0.5. So we're going to have a dipole-dipole. Hopefully for CH4, you were also thinking this is a tetrahedral molecule, not much difference in electronegativity, and London dispersion would be your only intermolecular forces. So if we were going to look at what's going to evaporate easier, oxygen and carbon tetrahydride would evaporate more quickly than something like phosphorus trichloride. Moving right along, let's take a look at some solids, some various types of solids. Of course, a diamond is carbon atoms repeating and repeating and repeating over and over again. And this is a network solid. How about this one? Oh, well, I think I advanced the slide too quickly. So this is a metallic solid. Remember, metals don't want to hold on to their electrons. They just want to give them away. This is why metals are good conductors of heat and electricity, because they allow their electrons to just run wild. So these positive circles you see here would be the protons in the nucleus, or the nucleus of those atoms. How about this type of solid? Hopefully you were thinking ionic, positive and negative ions shown in a repeating pattern. How about this one? CO2 molecules. Not the same atom repeating over and over again, but molecules. So this would be a molecular solid. C and O are both nonmetals, and so we've got a covalent bond there. And so remember, molecules are the smallest particle you can have of a covalent bond. So if we just had one of these CO2, that's called one molecule. Again, molecular being a very specific term there. All right, how are you on the phase change diagram? Well, let's take a look. What are the states shown here in A, B, and C? Hopefully you were thinking solid, liquid, gas. Again, I always think about water. Water is a solid at low temperatures, is a liquid at higher temperatures, and a gas at even higher temperatures. What are the names of the process when water turns from A to B, A to C, C to B? All right, let's see how you did. Do you think of melting, sublimation, A to C, a solid to a gas, and C to B, condensation? All right, where is the critical point? Of course, that critical point is right there. So hopefully you are thinking about that. And there's our triple point, as you know. So taking a look here, what property of a gas is shown here? Hopefully you are thinking that gases can be compressed to occupy smaller volumes. How about here? The gas molecules or particles are spreading out. Remember, that's called diffusion. They're diffusing or spreading out. How about here? As these gas particles are colliding with the sides of their container, they're exerting pressure as they bump into the sides of their container. All right, how are you on these pressure conversions? So I did just review the test, and you will be given the conversions that you need. Take a moment and see if you can convert 730 millimeters of mercury. Notice that decimal point, so this does have 3 significant figures in our measurement. Can you convert that into pounds per square inch and ATMs? Great time to pause the video. All right, how'd you do? So hopefully you start with your given, use your conversion factor, and get 14.1. Same thing for letter B, just a different conversion factor, so a little less than 1 atmosphere at that 730. And that's typically what happens when we have a rainy day. Our air pressure comes from the weight of the air and gravity pulling on that. All right, 2 most abundant gases in the atmosphere, nitrogen and oxygen. What would the air pressure be from the nitrogen and the oxygen? Again, a great time to pause the video, see how you do. Hopefully, as you were looking at those measurements, the first thing that came to mind was that those are pressures. And so we're looking at Dalton's law of partial pressure. Hopefully you also notice that each of them is measured in different units, so you've got to convert to the same units. And the other gases, of course, in the atmosphere. And so all to the same units. And that can be a tricky thing. And so I decided to convert my millimeters of mercury to atmospheres, obviously. And I've got 0.7803 atmospheres from the nitrogen gas. I chose to convert my pressure from my oxygen also to atmospheres. And 0.2 atmospheres of pressure from the oxygen gas, and then the other gases were already in atmospheres. So I simply add all of those up together, and I get our pressure to be 1 atmosphere, which is typically what we're under. That is what we would call our standard pressure, 1 atmosphere. All right, keep in mind that gases are standardized. We do have a standard temperature and pressure, and those are often referred to. You do need to know what those are. The standard atmospheric pressure, of course, is 1 atmosphere, as we just mentioned, and then temperature would be 0 degrees Celsius, and so that would be 273 kelvins. When you're dealing with gases, you're always converting those temperatures to kelvins. Remember that 1 mole of a gas at that standard temperature and pressure is 22.4 liters. All right, so what would be the mass of helium in a round balloon at standard temperature and pressure? Again, 1 atmosphere, 0 degrees Celsius, that has 6.25 liters of helium. Great time to pause the video. All right, how'd you do? Again, hopefully you started with our given. And using the 22.4 liters equals 1 mole of gas at standard temperature and pressure, hopefully you converted to moles of helium. And then to get from moles of helium to grams of helium, your molar mass of helium, keep in mind helium is not one of our diatomics, so we don't need to double that molar mass. Then go straight across the top, of course, and multiply. Divide by 22.4, and you get 1.12 grams of helium. All right. As I've been reviewing some of your work recently, I've noticed that some of us are still struggling with going through a problem like the one we just saw and recognizing the various variables that we use when we're talking about gases. So take a moment and see if you can recognize each of these. All right, how'd you do? What'd you say for number 1? That's 435 kilopascals, by the way. Hopefully you were thinking pressure. Generally, pressure is going to need to be converted to ATMs, atmospheres, when you're dealing with gas laws. How about 2.3 liters? Hopefully you were thinking volume. How about those grams of oxygen? Yes, you can get that into moles. Keep in mind that as you're doing that, oxygen is diatomic, so you would need to take your mass and divide by 32 grams per mole for oxygen. How about 47 degrees Celsius? Hopefully you were thinking kelvins in temperature, just add 273. And our 74.6 milliliters, hopefully you were thinking volume. But again, you're going to need to convert that to liters, so that'd be 0.0746 liters. All right, here we go, some solution vocabulary. On the Unit 3 test, there is some matching with some of that solution vocabulary. So there's a lot of solution vocabulary. So I'm just going to go through these next 12 slides pretty quickly, and then we'll go over the answers. Jot down your ideas. There are no pictures on the upcoming test, but I feel like when we're dealing with solutions, pictures can be very helpful. How about this one? Comparing these 3 solutions. Same solute and solvent, but 3 different solutions. How are they different? How about this one? How about number 6? Something's very important that you do need to know. 7. 8. This solubility curve, you do need to know that. 9. 10. Same picture as 9. 11. 12. And I lied. I said that there were number 1 to 12. I actually added a 13th picture at the last minute. All right, so let's see how you did. So what'd you say for number 1? Hopefully you said this is obviously a supersaturated solution, because I can see there's solute at the bottom here that is not dissolving into the solution, and that could be because our solvent is already full of solute particles. There's no more solvent to go down there and pull that solute up. All right, hopefully you were thinking that A is dilute and C is saturated. The only way that I can say that C is saturated, now B may be as well, so you could argue that, because I can see there's solute at the bottom here of C. And then I would say that A and B, by process of elimination, would be unsaturated. All right? Hopefully you thought number 2 shows a solid precipitating out. Solution number 1 could have been heated up, so that way all of the solute molecules or particles were moving around and actually in that solution, but it does look like it's way full of solution or very saturated. 3 looks a little unsaturated, maybe dilute. All right, what do we call this for number 6? Hopefully you were thinking aqueous, and we use the abbreviation AQ. Super important that you are aware of that when you're looking at chemical equations. Number 7, hopefully you were thinking that for a solid solute dissolving in a liquid, solubility increases with increases in temperature. It's opposite for gases, of course. Like, we're not going to leave our soda sitting outside on a hot summer day or in the car even. All those gases will bubble out into the air. All right, so what'd you say for this one? So 50 grams of potassium chloride. So I first have to find potassium chloride. Go over to 50 grams. See where it intersects the line. And the question asks us about at 50 degrees Celsius. So obviously that would be above the line. And so that's going to be a supersaturated solution. How about number 9? Hopefully you thought, yes, this solution is being diluted. I noticed that the number of particles doesn't change. There were 6 solute particles when we started with our solution, and even though we added more solvent, it's still 6 solute particles. We've got a concentration change, but we have not changed our number of solute particles. All right? These are called colligative properties. These changes to solution. These are things you already know, because if you're boiling a pot of water and with pasta, you're going to throw some salt into the water so that the water will boil at a higher temperature, boiling point elevation. We also know the same thing in the winter because we put salt on our roads so that instead of the water freezing at 0 degrees Celsius, it's going to have to get much colder. So that salt works here on Delmarva, but it would not work in other colder parts of the country. All right. Obviously, our solute is insoluble. The solvent and solute are not mixable. We'd call that immiscible. Remember the rule for solutions that like dissolves like. And number 13. So if these were 2 homogeneous mixtures, you can still see the particles in the second one. Those particles are so large that they are disrupting the light going through. That is a colloid. Remember that other homogeneous mixture. Milk, for example, is a colloid. All right? How are you on solution concentration? Keep in mind there's 3 ways that we calculate solution concentration. If it's mass per volume, your volume must be in milliliters. If you're doing molarity, your solution volume has to be in liters. All right, so see what you can do here, then pause the video and come back and let's see how you did. All right, so for this tube of toothpaste, we're looking at a mass to mass concentration. So we simply need to figure out the mass of sodium fluoride in that toothpaste tube. So I've got my percent concentration and divide both sides by 100, then multiply by 221 grams, and we come up with that the mass of our sodium fluoride the mass of our sodium fluoride, which is not coming up here, is 0.0024 times 221. So 0.5304. So I would stick with 0.53 grams of sodium fluoride in that toothpaste. So obviously, and I'm sure it's I'm sure it's planned that it's a tenth of the allowable amount. Here's another one for you. I love some trisodium phosphate. That's what it's called, TSP. It's great to use on painted surfaces before painting. So see if you can figure out what mass of sodium phosphate would be needed to make this solution. Great time to pause the video. All right, let's see how you did. Hopefully you thought of that mass volume percent, and then I always remind myself that that volume must be in milliliters. And so I'm looking for the mass of sodium phosphate to dissolve in that solution. I have to convert my liters to milliliters. And then I found that 34 grams was my mass. So in order to make this solution, I would take way out, just like we've done in the lab, 34 grams of sodium phosphate, dissolve it in a little bit of water, and then using a volumetric flask, dilute that to 2 liters. Okay, a problem that I've seen recently from the State of Matter quiz is thinking about how many liters of hydrogen gas are required to produce 13.8 grams of ammonia. So take a moment, pause the video, and see what you can do with this problem. So how did you attack it? Hopefully you thought, oh man, I got to come up with an equation, and that equation has to be balanced in order to figure this out. And so I often like to write on there because it just helps me. So I'm trying to figure out how many liters of this hydrogen gas I need to make a certain mass of 13.8 actually grams of ammonia. And so the first thing I'm going to need to do is convert these grams to moles of ammonia. Then I can use my balanced equation to see that 2 moles of ammonia equals 3 moles of hydrogen, because then I can go to my moles of hydrogen. Once I get moles of hydrogen, I can go to liters of hydrogen at STP, because I know that at standard temperature and pressure, 1 mole of any gas is 22.4 liters. So I kind of have to plan out what I'm going to do first and then start doing it. So I'm going to start with that 13.8 grams of ammonia, convert that to moles, use my mole ratio, then 22.4, go straight across the top and multiply, then divide by 34, and I'm going to find out that it's rounded to 3 significant figures, and I'm going to need 27.3 liters of hydrogen. So how'd you do on that one? All right, here we go. Another concentration question for you. So pause the video and come back and see how you did. All right, so let's see how we did. So we need this buffer to increase the pH of blood. So what mass of the buffer would be needed to make 500 milliliters of a 3 molar solution? So don't forget this formula down here, that molarity equals our number of moles divided by our volume. And again, that volume is in liters. And so I'm simply going to I'm going to convert my volume to liters, and then I'm going to plug those things into my formula. Rearranging my formula because I know that my number of moles is my molarity times my volume. So pretty quickly I can have my number of moles of the chemical, use my molar mass to figure out the grams of tris buffer that I'm going to need. And I could keep that at 4 significant figures. So once again, I'm going to dissolve that amount, 181.5 grams of that tris buffer, in water. Then I'm going to dilute it down with a volumetric flask to 500 milliliters. Oh my. Now we've got a dilution problem because we're going to take that same Tris buffer, but dilute it down for a different patient. So what formula will you use for the dilution? Hopefully you were thinking this one. So great time to pause the video and see how you do. All right, let's see how you did. This is just a plug and chug. So you can rearrange your equation here to equal molarity 2. That big M molarity means moles per liter. And then simply divide each side by 3. And you'll come up with your volume 2 that you're going to need. So you're going to take 37.1 milliliters of the buffer that you had just made up and dilute it to 53 milliliters for the other patient. All right, how are you with solutions? Stoichiometry. I'm giving you a balanced equation here. So this is a reaction they actually do in a lot of third world countries to produce chlorine to disinfect the water. So great time to pause the video and let's see how you do. All right, so how many liters of seawater am I going to need? Well, let's take a look. I've got all my information. So I'm going to start with my liters of chlorine gas. I'm going to use my 22.4 liters equals a mole because we are at STP. Then I'm going to use my mole ratio from my balanced equation. I'm going to figure out how many moles of sodium chloride. Then I'm going to use that to determine my number of moles. I'm taking my number of moles divided by my molarity is going to give me my volume, and I'm going to have to put that into scientific notation to keep it at 2 significant figures. So I'm going to need 2 million liters of water to make this work. All right. I'm hoping that you're ready for the test. Things I would encourage you to do to be sure that you can practice recognizing the various measurements for gases. Practice those gas law problems. Know all those processes of change in the phase change diagram and how temperature affects that. And review the vocabulary. And then I believe you are ready for that test.